The other guys, I know you probably haven't been here, but it's German, you have been here before?
Ja. Danke und wie gesagt, es wird
Sie hatten mir das ja
hoffentlich
erzählt,
so heiß,
genau, Sie waren beim Kollegen Ecker da.
gegessen, wie es Gut. Sorry.
Ja, sorry, das ist
Gut. Jo, ciao.
Ja, ich glaube, also
So.
sind alle schon da, dann wird man starten, oder?
Jo, sorry for the telephone call, but it was a little bit urgent, so okay. So wie ich es verstanden habe, I have to try it in English because we have 1 or 2, 3 persons from Ireland.
It's more 8 or 9.
8 or 9? Really?
Yeah.
Who is from? Okay. Well, I hope you understand me. My English is horrible, but
No, it's fine, I know.
Mr. Frey will help me if I get problems or I miss some words. So, okay, first, welcome to the laboratory. We are here a little bit different like the others because we are in the electrical, wie sagt man da, Elektrotechnik, electrical
Electrical
engineering,
engineering?
but we make mostly mechanical.
Maybe I can comment, probably there are even people here from the mechanical engineering department.
Oh, that's fine. So I can relax and you can tell us what we are trying to do here.
I just have to warn you that there are some experts.
Oh, fine. Well, then I have to take care what I'm telling
At
you.
least they know more than me, that's for sure, in that area.
Okay. Now the reason why you are here, as I've mentioned.
Maybe I can comment on the reason, or
You
go ahead.
have to take some wie heißt nochmal simulations, and therefore you need data. Now you are here to get these data so that you can do this simulation. So therefore we try to make a tensile test. Most of you know what it means to do this. We will do this tensile test on very small pieces because in the for the electrical components to make I say these things, motherboards are like this. You need Alloy ist ja Legierung.
we need a special material which are important also for assembling MEMS. So
Load, wie sagt man Load?
the material which you, to solder.
Solder. And years ago in the solder we had plumb and tin, and plumb is not so good for our health, so the decision from the government was to eliminate this. So there were many ideas of Ersatzwerkstoffe, other materials to compensate this, and I and my boss, the professor who was years ago here.
You call him boss.
Yes, because he
Good to
told
know.
me what I have to do, so I was not allowed to say I don't like this work. Look for another guy. So, and therefore they had many different. Alloys, aber das sind ja nur Legierungen. And to know what this material how
How it
can I say?
behaves, or
Naja, was das
Sag mal
Material macht. Our job was to get die Materialkennwerte. Ich habe es gerade nachgeschaut.
the material parameters,
The
for
parameters
new,
of these materials, we have to make many tensile tests to get the yield strength, the A modular, the strength of the material, and you know this, but I let it go around so you can see what we are talking about. And to do these tests, you have create samples for the tensile tests. It's not made after German norm. How is it called? In Germany we had the DIN norm. Now it's European.
Is it like a manufacturing standard or?
like regulation documents which describe.
It's a regulation how the sample has to be, the diameter, the length, and so on. But this is made. We have tried to make the samples as small as possible, because if you look at the parts, we are talking about not the parts, but
Soldering joints.
sorry,
Soldering joints.
for the soldering joints, and with your eyes you can't see it anymore. So the goal was to make the samples as small as possible, because it's a big difference if you have such a sample or this one. And these samples we will test today have a diameter of 0.91 millimeter. We tried to go down to 0.5, but this material is very soft, so you have nearly no chance to get this out of the Gussform, out of
The
the
cast,
casting form without damaging the material. So this was our limit.
just also for my information, it has to be cast, or could it be machined? You know,
Machined.
a reason probably it has to be cast.
It's difficult because it's so soft, this material. This you can make with a machine, but this one,
I see.
no chance. We have made Like this, with this, we had the possibility to make 4 samples with one cast.
And you produce them yourself, or?
Therefore, we had students.
You let them produce.
Yes, because it's a horrible work. So,
That's why it's for students. Makes sense.
but they got money for it. So, and 2 or 3 points more at the exam tomorrow. Okay. What do we need else? What else do we need for the test? We have the sample and we need a machine. This one. In German it's called Universalprüfmaschine. It's translated universal
Like generic machine for many
machine. This means you can do tensile tests, or you can make
Pressure.
compression tests. Thank you. And therefore universal.
But it's not universal in the sense of the load. You couldn't do the tensile test on this structure. That wouldn't be possible. It's especially.
With this machine, we have limitations, and the limitation is not the machine, but the samples we need for measuring the force. In German, it's called Kraftmessdose. I don't know in English. It's
The device who measures
the force.
the
How
stress.
is it? Yes. How is it called in?
Strain.
The thing at the bottom?
This one is. It's.
It's certainly the wrong translation, but it's like a box which measures
Yeah.
the stress.
Yes.
And it's called wie gesagt, Stressdose?
Kraftmessdose.
Probably there is an exact
Measurement. Force
translation.
measurement device.
Yeah.
And for these machines, we can only measure until till 10 kilonewton. It's not so much, but at the university we have different places with different kinds of machines. So if we need more, we can go to the Maschinenbauer, to the mechanical engineers, or to die Bauleute,
Building construction.
laboratory. They have bigger machines.
But for the purpose of that soldering material, that is completely suitable.
Yes, because what do you think? How many force do we need? 1 Newton, 100 Newton, 1000 Newton?
Probably less than 1 Newton.
It's a little bit too less. A little bit more.
10.
A little bit more. But the direction is, it depends on 40, 50 Newton. It depends what's inside, because we have different materials. It's tin, silver, copper, with different combinations, and it makes different. So we have ranges between 40 newtons and 140, 50 newtons. So I don't know what I've prepared here, so we have to see
I told you.
what we get results.
I was not aware of this, but you say that it's made for up to 10,000 Newton
Yeah,
force. That means we using only the very small range in the lower end.
no.
No?
This is the big load cell, but we are working with the small down.
The question I addressed, because otherwise we probably will have a problem with the resolution if we just use from that size only a
Yes.
small fraction.
And therefore we have another piece here, and this one goes from 0 to 200 Newton.
I see, that fits.
And
why I
that's
get the
in the
resolution.
range. The company says it's not a problem with this big one. The resolution should be the same if you are working at 10 Newton or 10,000 Newton, but I don't believe this. That's a trick to sell the components. If you are if you want to do it right, you have to be somewhere in the middle between.
Can you use both sensors simultaneously?
No, it because we can put there 10,000 newtons. We have nearly no influence for our test, and there are two cables, and we have only the possibility to plug in one cable. So
Ah.
the black cable is plugged in. Therefore, we see only the small piece, the value of the small.
The electronics is the limiting, right? It's not the mechanical.
The cards inside.
Interesting, yeah. Because otherwise, obviously, you could check what is the difference, but if you cannot measure simultaneously.
You still could check. You could run once and then change it, run again.
We can change it, but we have to shut down the whole machine to plug out, plug in, because in the here inside there's something, a small program, and if we put it out and the machine is running, we can have we can have problems with the programmation. Okay, are there questions until now? Okay, then I would say we try to get some results. Therefore, before we are starting, the material is very soft, I've mentioned before, and normally you have pieces like this where you can einklemmen, how is it called?
Mount.
Mounted, where you can mount the samples in it. But if you are closing this system, you become force on the sample.
Stress inducer.
And for our samples, this is a problem, because you don't know if you are damaging the sample. For this one, it's also not optimal, but it's okay. You can work with it.
What is it?
This is
Some other material where you want to have the material.
it's plastic, so it's a little bit stranger than our alloys, and to be sure that we are not damaging the sample, we have create something. Ah, we have made a system where we are guaranteed that there's no force before beginning the test. So the head has a conus, and you can put it without force in it. And the same is here. So that we are sure that the sample is okay before starting the test.
If you say we did it, that was also done with some examine works or some practical works or some.
This one has made a friend of Professor Villard, because that's not so easy to make this mounting systems. You need practice for it, and we have students who have Ausbildung, who have made the education, but to find these students is not so easy. And years ago, it was a matter of time. So the person who made this for us has become money for it. So we were sure that the systems are made in the way we wanted to have.
From this, by the way, you see, I'm not an expert. I wouldn't have expect any problems with such a part. Is it possible to explain why it's so difficult? I mean, I would assume you just need to find a proper shape which does not cause stress. So it's a matter of designing the shape.
I think like designing the holder. It's
The
just
holder,
so tiny.
yes.
Yeah, just so tiny.
Yeah, why is it such a problem?
Not-
Because I'm not an expert.
Not
but
that size, the tiny one.
yeah.
It's so small that you have to machine it so precisely.
Und du musst auch innen rein dann den Konus dann machen.
Also it's a matter of machining. That
Yes.
was the problem, not
Yes.
the design, but
No.
to make the produce it.
To produce
So
it, yes.
I misunderstood. Yeah, because the design is in a way straightforward,
Yeah, yeah.
but how to understand? Yeah.
Mhm. Okay. So-
Is it something today you might do with 3D printing? Maybe the material isn't strong enough.
That's the problem.
Yeah.
Professor Eckert, don't know if you know him. He is from the material side, and he always tells me you have to take care what you are taking for the tests, because everything what we are making here, the material is bending,
Flexible.
is flexible, yes, and so we have to take care the machine is stronger than the material you will test, and this is often a problem, because with our samples, okay, it's easy, but with this one you get problems. Therefore, you take a big machine to guarantee that the machine is stronger than the sample you are testing. So to
Special.
make such holders with 3D printing, it's not so easy. There are not many materials you can test with it, because your holder breaks earlier than the material itself.
The motivation, we were happy to be invited by you to come here, was we discuss all these things from the view of MEMS. And in case of MEMS, obviously the materials are the soft one. So if you would only handle that one, then 3D might be an option, because the materials are soft.
Yes, but
No reason to do anything, you have your solution.
I've always been told, take steel and not aluminium, and if I come with something like this, then I think Mr. Eckert will be very, very sad.
No, but just to understand, I mean, for MEMS and PCBs, obviously steel is not important. It's not an issue. So if it
It's compact. So there's a certain range of where it'll stretch, whereas these will just have a critical fill and snap like that.
Yes. But I mean, the motivation to investigate that type of material is original from the PCBs, like you explained. And in that context, we don't need steel. The steel is not the typical material for MEMS, so to speak.
Okay,
But, I mean, obviously you're on a broader field.
yes.
That's the case. But if you would be restricted only to PCB, then steel is not an issue.
Yes. Okay. Then I push the button. What you can see is on the screen how the curve is growing. You wouldn't hear something on the tensile test. With this one, you will hear it if it breaks, but with the soft material, the machine will stop and you will think, what happened, is the test completed or not. So one or two. Yes. Okay, then I think we start.
So what parameters you have to configure? A load range, or what are the parameters which controlling this frame?
Die Zuggeschwindigkeit.
The velocity
The
also.
velocity of the machine is
The velocity in which it ramps up the force.
it's possible to do this adjustment. I have to look because, okay, it looks like a little bit different than the other ones. It means that the sample is, the elongation is very high for sample. The parameters are in the software hinterlegt inside, and it's made of the mentioned this DIN norm, and I think.
I mean, my question also addresses what we see on the axis. So you prescribe a displacement or a force?
This displacement, the velocity was 10 millimeters per minute.
I see it. Then I also understand with the velocity, that means at a certain time, a certain stretch, so to speak.
Yes, yes.
And what you, of course, yeah, actually you explained, I stood up, what you measure with this doser is the force. So you have to provide the stretch and you measure the...
We only measured the force and we measured the elongation, the way this is going down. Normally, you will measure in a small range like this to make the calculation, for example, for the E-module, and to get genaue,
Precise.
precise results. But for today, it's okay if we are taking the way of this. It's in German. It's called Traverse.
Sorry, when you say you measure the force, do you mean as the machine is pulling it out, the force is increasing?
Mhm.
So
How is
that
it?
what you mean is that the force is increasing as there's more elongation? Do you get what I mean?
Is it one force the whole
Is
time,
it
or
like
does the
constant
force ramp
or
up?
is it force like being affected by time? So as the machine keeps on going, the force keeps on increasing. Is that how it works? Or?
I'm not sure if I have understood it
Like, is
right,
there
but
more?
for the machine, there is an fixed value for the velocity, and it don't depends on the force.
Okay.
We are only measuring the force over the time, and the machine has the velocity elongation per minute.
When you apply,
When you apply, do you start off at 50 newtons, or does it range up like 5, 10, 15, 20, 50
it
breaks?
hits a max.
It's not driven by
It's
force, it's driven
position.
by the velocity.
Yeah, oh, you get the position and then you determine
Yeah.
the force. Yes,
That's
And
a-
the force is there are
So it doesn't
hundreds
move,
of
and then it
values
measures.
of the force measurement.
So you set the position, it changes over time, and as a reaction, you measure the force.
Mhm.
So
Yes.
the force not prescribed as a like a
It is
response.
velocity.
That's also something I screwed up in the beginning. Maybe because of this, I anyway set all of us in the wrong direction.
When back home, we are normally do it with the force.
I,
We normally
you
set the force.
you set the force
And then you get
measure-
the
I
elongation.
see.
Yeah, you get the elongation, so that's why
Interesting.
it's-
Ah, yeah. That actually, intuitively, I also would assume something like this.
Yeah.
But because he mentioned that they have sensors for the force, obvious makes sense that they give the distance. Another question, you mentioned the velocity. I would assume in ideal world it should be independent of the velocity. I mean, if you make it very slow, what is the difference? Between making, I mean, if you are too fast, I can imagine, then something goes wrong. But if you be slow enough, it wouldn't change anything if you be slower. Is that correct? Or?
Yes, because we can't drive so slow that creeping will be a matter. For this material, it's called high temperature Hochtemperaturversuch, high temperature
Experiments, yeah.
experiments, because this material schmilzt.
Melting?
Yes, thank you. Melts at 220, 240 degrees, and the temperature we are doing these tests is 22, 24 degrees. So therefore, it's high temperature experiment we are doing with this material.
How is this defined? Because it's so close to melting point.
Yes.
Is it defined in percentage in Kelvin scale from the melting point? Or?
It's called in German. It's called homologe Temperatur, and it's a quotient between melting temperature and experiment temperature. So the temperature in Kelvin, not in grad Celsius, but it's doesn't matter so much, and the difference between 220 is small comparing to steel with 1000 280 degrees to 20 degrees. So that's the reason why it's called high temperature experiment.
Actually, if you would use that MEMS in automotive application, as I remember roughly, there are specified temperature ranges, maybe from -10 up to 110 or something.
Minus 40, I think,
Whatever,
to 80 degrees.
To 80, yeah. Then, I mean, ultimately you want to know from that material data, is there a problem with oscillations or loading? So, consequently, you probably should make determine these parameters for the lower end, maybe for the higher end, or maybe have arguments it's only critical for lower or higher end. Probably higher end is more critical, huh? For losing, or because getting more soft. But that would mean you have to measure at 80 degrees.
Yes, and there were experiments. We made creep tests on different temperatures. On the side there are curves who shows these experiments. We did it on 20 degrees, 50 degrees, 100 degrees, and we made creep tests, not tensile tests, but creep tests. It means we took the sample, hang on a defined load, for example, 10 Newton, 15 Newton, and then we are waiting to see what happens with, and to get the informations we need, this elongation, we have to be very precise, and this one is not very precise. Therefore, we had this one. It's called laser extensiometer. With this, you can measure the elongation very, very precise in micrometers. Yes, to do this, you have to do a lot of work in front to make sure that it will work, because there are many influences who can damage the measurement. For the measuring of the load, there are these, I call it load cells, and it's the same like this one, but if you look at it, it's a little bit damaged, so therefore I have opened it so you can see inside how is it working, because we are also at the electrical part. It's called, in German it's called DMS. Yes.
Strain gauge. Probably a strain gauge, yeah.
So they are very thin copper wires, and with the force, the current and the resistance of these copper wires will change, and this is what we are measuring. And if you make a calibration, you can compare the changing of the resistance, or you can nicht compare, nicht vergleichen, zuordnen. You can say a changing of the resistance from 0.1 is, for example, 1 Newton. I can take it out, so
That setup in general can be configured to also make the temperature measurement? Probably not. It's not intended for that. You cannot make at 80 degrees. You would have to build something.
Normally we can, because at the backside there is an oven, but it's not so easy because the load cell has to be outside of the temperature, because if you put 80 degrees on the load cell, there will be many changes. So you have to adjust it new to make a new calibration, and that's nearly not possible. So theoretically it's possible, but it's not so easy to
Realize it.
thank you, to realize it. I'll show you the sample before testing, and then you will get our sample after testing.
Okay, looks pretty solid.
So you have the comparison. Because of the soft material, you have seen it on the screen. We have a very large elongation in our sample has an elongation of about 4.5 millimeters, and that's a lot because we started at 7 millimeters, and elongation of 4 millimeters is more than 50%. So that's, for steel, it's not possible, but for our samples, it could happen.
I'm not sure what you planned. Do we do another experiment to get an idea about the variation, or was not planned?
If you want, we can.
I would not. If you guys interested, because
Sure.
maybe just to get a feeling how reproducible it is.
That's not so easy.
But that's why I asked. If it's a big thing to make that, then
I have to explain the samples we are using. Normally I wouldn't take it to get the material parameters, because we have checked the samples under the microscope, and the samples have to be,
you make like a quality insurance. You check for several
yes,
things, and then you select which is a good sample and which not.
and which is
So you
not
kept the
good.
bad one for us.
Yes, because
That's okay.
I have a lot of samples what we
Yeah. No,
normally not
makes it-
use, and for the practicum, and to show how it's working, it's okay, it's enough. You will get different data for your calculation, so you don't have to be care about this.
But it's anyway interesting because it underlines it's a challenge to produce a good sample. Because if you just do it and take all of them, or at least let's see what the experiment provides us. If you have a large variation, and also interesting, you say you can distinguish regarding the quality by the microscope. So you just optical observation, and you can say it's a good sample.
Yes, normally we have to make jetzt fällt mir nicht mal mehr deutsche
So.
Röntgenaufnahmen.
X-ray.
Yes, normally you have to make X-ray
That's something I would expect. That's why I was wondering that you could do it on the light microscope.
If you have time enough, you can count the samples.
That's why I have students there.
And the problem is that's way too far. We only
No, I understand that, but just to find out what would be the correct way.
Yes. Because at the university we have no possibility to do.
We are poor people.
Yes, it's really so. These machines here are from Siemens, and we got them geschenkt as a gift. This machine.
But it's a poisoned gift, you know, because you
You have to work with it. Yes.
no, you have to finance the support. So always running around to get the money.
Yes, that's sometimes it's a big deal because to take someone from the company to look after the machine. I think 5 years ago they want around 200 euro an hour. So take the service makes 1,500 euro, and you can ask Professor Frey how many euros we become for one semester, and that's
I'm
not
only doing
so
software, no hardware, you know.
much. And software is also expensive,
No,
but you have the connections.
No,
That's the reason why you are so
We're leaving
cheap.
the topic. but also at the time when you made the samples, you did the experiments, what was the intended result for that? You remember, like getting the Young's module, definitely?
Yes, the goal was to get the Young's module,
Yield stress?
yield stress, E-module, but E-module it's to get the E-module you have to make a cycling test, and we have no chance to do this because this test is in a very low range of you have
actually,
to be inside of these
Hooke's laws. The Young's module, the E-module, I would expect, maybe I can approach, the information should be here in that straight line,
Yes.
shouldn't it?
Yes,
So, and why you need to make a cycling?
that's the norm, German norm, and
So you have to go up and down to see that it's the same
and,
slope.
and then you make the
The average?
the average
I see.
of this, and
I have to ask because we exactly extract that parameter, and I learned we do it the wrong way because we don't have a cycling. But anyway, we have to.
yes, but
just use
it's okay to take one parameter,
Yeah.
and not with this
Not the same,
cycling
yeah,
test. But you have to know that's not the correct way.
Yes, yes.
But that's the only possibility. To do these cycling tests, you need different holders,
yeah.
different setups. Yes, only to be mentioned.
And that parameter, who demanded or who used the parameter? Simulation people or what happened to the parameter?
It's a very good question. We were in a Verbund
And a research project,
on a project, and
you had to deliver the parameters.
at the end of this project, some people wrote very very
Thick?
thick book, and this book was sent to the government because the money came from the government.
That's why it had to be thicker.
Yes, because as if I mentioned right, the government paid nearly 10 million euro for this.
So the answer actually is you provided the E-module for the government.
At the end, no, because the government paid.
Who pays? Who gets it? Of course.
The money. The interesting side is the money goes to Siemens, and Siemens gave it to
The small guys.
yes, to the people who were
Doing the
also
work.
involved in this complete project. And there were many universities and many companies who are involved in this project. Bosch, Siemens, Daimler, University of Berlin, Dresden, we were involved. So many people, and from this 10 millions we only got nearly 1 million for the machines, for the people who were who have to be paid, and so students got most of the money. No,
They made the work.
they made the work, but this was the cheapest part of all. Okay, then we try a second, this one, to see. Second, then position, and then go.
It looks similar.
It looks similar, yes. Oh, more than the first one, nearly
Even more.
more.
But until the point where it's difference, it's approximately the same. Huh? So the
Yes.
difference is particular at the very end.
There are many parameters who take influence of the results, the grain size, the temperature, right, the velocity was the same now. What we don't know is if there are something included in the material. So therefore we have to look inside, and this possibility we don't have here. Maybe that the first one I've made 10 years ago, it was a different material, because today we have tin silver copper with 3% silver and 0.9% copper, and maybe we had other combination. This, for example, has 4% silver and uh, 1.2% copper. So it makes a big difference. I have only put the data for the name, so I don't know what kind of material we have been testing 10 years ago, but it's not necessary to know. For you, it's important to get the data. Don't know.
I think you already sent me data, which I will
yes.
use. Just to make sure again, the data, what is on the axis, in what units? Is it the distance on the x-axis?
What we are seeing now is the elongation in millimeter and the
Millimeter.
force in Newton. And to do the comparison, you need the elongation in percent and the force in Newton per square millimeter or inches, or I don't know what's.
So we need to start the initial length to calculate the percentage value.
Normally, we have to look if the calculation is made on your data. This I don't remember.
Yeah,
but
we can check it.
We can check it.
Yes.
To do the calculation for the elongation, you need L0, the
Initial length.
initial length, and for this samples, it's every time 7 millimeters. So by 4 millimeters, 5 millimeters.
You know what is surprising for me? You remember the last lecture when we discussed about this crazy C with 81 elements, and at the end, you know, we measure something in percentage, and we get everything from there. This is how would you could you determine the Poisson ratio in that experiment? No.
No.
No. That would require a different setup. The idea would be now, with this data or similar data, next Wednesday, we extract the parameters as good as possible, and then we use that parameter to feed in a geometry which hopefully is similar to that one, and then we make a non-Hookean plastic simulation just
It's only a cylinder. Diameter 1 millimeter and the length 7 millimeters. So I think to create the Körper,
the geometry. I think you got me the data, so we have to put it in COMSOL. And for me, the motivation was like, if it's relevant in context of MEMS, maybe some PCB gets involved, then the relevant question could be, if you have certain loads like acceleration profiles, how many cycles could you make if you have forces which brings you into the plastic range until you get some damage, some rupture. So for that you would need to have that parameters to do the plastic simulation, and then you would cycle it, and ultimately you might get an idea how long it can withstand certain load profiles. So that would be the conclusion from where we go from here.
These samples were made for soldering, you said?
Yes.
Yeah. Why is the steel necked and the other samples are not? That is just where it's going to break.
Sorry, once again.
The steel is necked?
Because the test was interrupting only to show what's happening with the material. And this is made by the colleague at the mechanical engineering, because they have the great machine. And I took the sample only to show the students what's happening, because at the small pieces you can't see it. So that's only for
Demonstration.
For these one who have never seen what is happening with the material. Normally you are starting with this, and you can put it together, and you can see the elongation and how is it called if it gets
Necking.
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 Ah, necking makes sense. Like these.
Necking, okay. I try to learn. Okay, and that's the reason why we have this here.
Back home in Ulster, you probably have more machines to operate something like this, and not the small solder samples. Or
I think ours is a similar size to that, but there would be like a research facility in Belfast that you would partner with, and they have big, huge ones.
I see here.
Mm.
But the material you're looking for is more steel, not such strange thing as soldering
And
here.
we do a bunch of things, like a lot of plastic samples and stuff.
I see.
Oh, plastic, okay.
Next time I visit your place, I should go and also have a look.
Okay, are there questions for the moment? I think,
We are almost perfect in time,
okay,
so I would say thank you very much, Arthur, for having sharing the time with
I
us.
hope it was okay for you, because you see, with my English, I missed the practice, so if Mr. Fry will come more
often.
times with students,
You know, my
I
advice-
get better and better. I
These
hope so.
people also help me out in my lecture, you know. I also sometimes know what is this, and then they always tell me. So, but I have more interaction with them than you, so it's perfect.
Okay.
Perfect, yeah.
Then
Thank
thank you.
Thank you.
Fine.
Then see you lecture next Wednesday. The nervous acquisition.